In this lesson, we are going to look at real and imaginary numbers. A set is a collection of items called elements. The rules of 8-ball divide the set of billiard balls into 3 subsets: solids, stripes, and the 8-ball. A subset is a set whose elements belong to another set. The empty set, also known as the null set, is denoted with a phi. This is a set containing no elements. The diagram below shows important subsets of real numbers. So each of the ovals is a subset of the rational numbers. So all of the ovals that are contained inside of another oval means they are also part of that subset. So let's look here. When we are referring to real numbers, you will see that we have an R with a double bar over here. Rational numbers have a symbol of Q with double bars, Z for integers, W for whole numbers, and N for natural numbers. So if we talk about two different sets of numbers, we are subsets of real numbers. We have rational numbers, can be expressed as a quotient or a ratio, or I want to use fraction. All of those, oops, forgot my T. A quotient, a ratio, or a fraction of two integers, so they can be positive or negative, where the denominator is not a 0. The decimal form of a rational number either terminates or repeats. Examples being 1/2, that's a ratio or a fraction. 0.5 terminates because it ends at the 5. -4/3, that's a negative fraction. Or 1.3 repeating. On the other hand, irrational numbers, such as √2 and pi, cannot be expressed as a quotient of two integers, and their decimal forms do not terminate or repeat. However, you can approximate these numbers using terminating decimals. So when you put a square root of 2 in a calculator, it will give you a decimal and it will stop. That doesn't mean that it actually does stop. It just terminates the decimal for you. So let's look at the numbers inside of our real number set. We start out with natural numbers. So those are things that you used when you were little and you counted. So you had 1 cookie, 2 cookies, 3 cookies. Those are things you used naturally. You counted. Positive numbers, whole numbers. And then you were introduced to something called actual whole numbers. So natural is 1, 2, 3, 4, 5, 6, 7, all the way till infinity. Whole numbers are where you tried to eat a cookie before dinner, and mom, dad, grandma, grandpa, aunt, uncle, sister, brother said, nope, you can't have any. So they introduced you to 0. So 0 is a whole number, and since this whole number also includes natural, then natural numbers are part of whole numbers. So whole numbers include 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way till infinity. Then we look at, okay, now we get to the point where we have to pay somebody or we owe somebody something. So then on this outside ring here in the blue, we introduce integers. So those are the opposites of our whole and natural number. So all of those positive numbers that we had, now we have the negatives as well. So we have -5, -4, -3, -2, -1, 0, because that's a whole number. And then we also include natural numbers, so that means all the positives, 1, 2, 3, 4, 5, 6, 7, 8. So from negative infinity all the way to positive infinity, as long as we don't have fractions, then we have integers. So at this point, there are no fractions, decimals of any sort in our numbers. So if I have an integer, it's positive and negative whole numbers. Whole numbers are 0, and all the natural numbers, and natural numbers are just 1, 2, 3, 4. So if I have a natural number, then it is also, so if I have 2, 2 is a natural number because it's contained within whole numbers. It is also a whole number, and because that whole number circle isn't contained in integers, it is also an integer. And then outside of that, we now have rational, meaning ratio, meaning fraction. So now we include all of the decimals, fractions, repeating decimals, terminating decimals. Those are all rational numbers. So all the numbers that we deal with on a normal basis are rational. On the other side of that, you can be rational or you can be irrational. So we have this other piece of real numbers that is exclusive of rational. So you're either rational or irrational. Irrational includes those things like pi, because it does not repeat. E, because 2.7 does not repeat either. And if I have the square root of one of these prime numbers, I can't really have an exact value, so that doesn't repeat either. And then if I have a fraction with the square root of a prime number, I am also going to have an irrational number. So irrational numbers are those things that do not repeat, do not terminate as far as decimals, and can't be written in any of the forms of the rational numbers. And all of the rational and irrational numbers are contained within this big box here, that they are all real numbers. Those are the numbers that we have worked with for as long as we can remember. So let's take a look at, why do we have real numbers? Is there anything else? Well, yes there is. We have imaginary numbers. So imaginary numbers, we don't really like to write the square root of -1, and we can use that on a different coordinate plane to graph imaginaries. So instead of writing square root of -1, we're going to write I instead. And it is in italics I, and it really looks like that. It's just a fun little I. And then if you square a square root of -1, then I squared is equal to -1. So we will use that as we go forward, using I and I squared. If we have a complex number, that means I have a real component, so a real number, and then I have an imaginary component. That makes it complex. So real if I had 3, and imaginary if I had a positive 5i. So our real component is 3, and our imaginary component would be a positive 5i. Or we could have something like 6 minus 7i. So the real component would be 6, and the imaginary component would be -7i. We will use that later when we start working with quadratics.